Okay, so I want to start this class by asking whether or not there would be a difference between the test scores for my online students and the test scores for my students, my resident students, you guys. How would you do that? How could you figure out if there was a difference in the scores between my online students and my resident students? Two sample t-test. Is that what you said?
Yeah.
That's what it sounded like. Yeah, so two sample t-test. So two sample, we didn't say like two sample when we were talking about it. We had one sample and then we had two different types of independent samples t-test. That's right, because you guys are different groups. You're independent sort of one another. And I have nothing to pair you guys on necessarily. So do the tests for the online and the residents differ? I actually ran these tests this morning. No, they don't. I forget which group is doing a little bit better than the other. But if you run the t-test, there's no statistically significant difference in the groups. In fact, the p-value is 0.24, which means that there's a 24% chance that you would observe the difference that I did observe just due to chance under the null hypothesis that those means are exactly the same. Now, there are a number of different ways to think about scores, and there are a lot of students who take classes with the attitude that C's walk. Have you guys heard that? C's walk?
C's get degrees.
C's get degrees, that's right. So a C, any type of a C is a passing grade, right? And beneath the C is not passing. So maybe we could ask something like, is there a difference in the passing rates for the online students and the on-campus students? Does that make sense? Now, what type of variable is this? Whether they're passing or not passing. The test scores, this is a ratio scale variable, right? Because you have a true zero. Someone doesn't take the test, you get a 0. So scores are ratio scale. What is passing?
Category?
It's a categorical variable, right? So we can imagine that we have some categories, and we can create an outcomes matrix for this. So we have like class type, resident, or on campus, and also online. And we can also see whether or not our students pass or fail. So fails in this sense, I'm considering any type of a D a failure. Because if you're taking it, there's an option that students can take a course for S or U, satisfactory or unsatisfactory. So the satisfactory is like a pass, unsatisfactory is like a fail. So we've got two groups. So imagine that we have, I don't know, let's talk about percentages. How many students should be failing a given course, do you think? What percent? D's and F's?
5% maybe? 3%?
10 or 15, 5%, 3%. So if you think of, what percentage of people should be getting A's? 20%? 20% A's? So the distribution, this isn't pure, but imagine we have some continuous scale, and I'm just going to label F, D, C, B, A. So 20% up here, and maybe something like that. Is that what you guys are thinking? More or less. You know what this is indicative of? If you have distributions like this, you'll get distributions like that if you go to places like Harvard, and even some places like EOU, depending on the instructor probably. I don't know that for a fact, but I would guess. If you have a grade distribution that looks like that, what's going on? Curving? Not necessarily. It's a skew negative, right? Because the tail goes off in one way more than it does in the other way, and congratulations on getting that, because that's not really anything that we've talked about much. That's grade inflation. That is grade inflation. The average is supposed to be, by definition, if you read the handbook, is a C. So what the distribution should look like is something like that. Although it's probably a bit wider, so if you consider really bad Fs. And imagine that you can't get better than an A, it cuts off at 100%, which often when I curve scores, there are some students that get over 100%, but it's not like I can give them something better than an A, so they just end up with an A anyway, which is one of the reasons I don't do the whole plus minus things for the A's. But anyway, so we should have some distribution like this. And if you imagine things, so C is supposed to be in the middle, so I like to think about scores like that. So 20% A's, that's a ton. Maybe 20% A's and B's, that's a pretty decent number. So if it really is sort of normally distributed, you should also have 20% D's and F's. Now probably, in fact, I mean I can't guarantee anything, but usually the D's and F's, in my classes, there aren't as many D's and F's as there are B's and A's, so maybe there's some grade inflation going on in my classes too. That's what I get for offering extra credit. Anyway, let's say that there are 20% of the students that fail. And I'm going to just use that because it's going to make my life easier, okay? So now imagine that we have 100 online students, so I'm going to write down numbers instead of percents. And 100. So I have 100 resident students and 100 online students total, okay? So if we add things up, like in rows or columns, we're going to get totals. We can also add up the column rows, or the column totals. So how many people do we have total here? 200, great. So if 20% of our students are failing, how many students does that mean are failing in total?
40.
40. So we've got 40 people that are failing. So these things have to add up, right? So how many people are passing then? 160. Now, let's ask a question. So even though there's no difference in the distribution of scores that I've seen so far between my online and in-class courses, if there were to be a difference, what type of class do you think students would be less likely to fail in?
On campus.
On campus. Does everyone agree with that? You think fewer people on campus would fail? I think that might actually be true, because when I compared the distributions, even though they were statistically identical, there's a bit of information that I haven't given you guys. Almost no one has dropped the course that's in the on-campus course. That's not the same for the online course. I've had more people drop. What type of people are dropping? The failing people, right? So it's this self-selection. So I'm guessing, yeah, probably if we consider the drops as fails, maybe people who are online are failing more often. So let's say that we have 30% of our online students, right? That would just be 30 because we only have 100 online students. Now notice something. Because we have this number, we know how many online students failed. This means that we automatically know everything else, given these totals. All we have to do is some simple math. So how many of our resident students failed? 10. How on earth did you figure that out, Mr. Genius? 10 plus 30 equals 40. Simple. How many of our resident students passed? 90. How many of our online students passed? 70, right? So we found 90, 10, or 100 minus 10 equals 90, and 100 minus 30 equals 70. Let's make sure these add up. 90 plus 70 equals 160. Everything's perfect, right? Now we have this question. Does taking the test, or does being an online student actually, or maybe not, does it affect? Because we're using a chi-square and we haven't manipulated anything. I didn't assign people to be online students, right? So this is just a correlational study. Now, if two things correlate, that means that things aren't independent of one another, right? It may not be that one causes the other. It could be that something else is causing both of those things, but there's some dependency in there somewhere, either one causing the other, or the other causing the one, or something causing the both. There's some form of dependency in there. So what we're going to use to figure out if there's a dependency is something called a chi-square test. You guys heard of chi-squares?
I just did one the other day.
Just did one the other day in a biology class?
No, in emotional psych.
Emotional psych. Don't laugh. I learned about chi-squares.
Yeah, it was great.
I learned about chi-squares in biology, actually. So chi-squares are used all over the place. And they're used with a very specific type of data. Notice that what we have here are basically frequencies. Out of the time period that we were making our observations, so the end of the class, how many of the people fell into each of these different categories? So all we have here are just counts. This is very different. It's not the average score that a student got or anything else. It's just a count. So the only time that we're really justified in using a chi-square is when one person can only fall into one condition, right? So for this class, you are either an online student or a resident student. You can't be both, at least not this semester. You can take it online in the fall perhaps, but this semester you are one or the other. This semester, at the end, you will either pass or you will fail. There is no in between, right? So each person can only fall into one of these situations. So I'm very grateful that we have students who've done this recently. What is the formula for a chi-square test of independence? So chi, we're using the Greek letter, chi-square, yes?
Outcome minus expected squared over expected, I think, off the top of my head.
I usually don't refer to it as outcome, but observed.
Oh, yeah.
But what you observe is an outcome, so you're just fine. We're cool. So observed. We have some observations. And there's one more piece to this. It's not just observed minus expected squared over expected. Anyone know what the other piece is? What did we do when we found a mean? What did we do when we took a variance?
Oh,
what did we
it's the
do?
sum of.
Yes,
Sorry.
that's right.
I've got that.
But you remembered, good for you. So we're summing up all of these differences between what we observed and what we expected to observe. Now I want to point something out here because a lot of the statistics are very closely related to one another. Remember when we had this formula for variance and we had some, and let's do the unbiased one, and we had x minus x bar squared, or x minus the mean squared. Think about what the mean is. What is the mean? The average of all the scores. So if we knew that the mean height of students in this class was 5'8", and you gave me a blindfold and you said you had one of the students stand up, and I was going to get money if I fell within 2 inches of their actual height, what's my best expectation? What should I bet on? 5'8", right? The mean is the score that we are going to expect more than any other score if we don't have any other information. Why? It's the score that minimizes the deviations from the mean. And it's the score that minimizes the square deviations from the mean. It's the best guess that we have. So this x bar is like what we're expecting. And what we're doing is we are subtracting that from what we actually observed. So the numerator for variance is very similar to the numerator for chi-squared. And guess what? You know how we talked about the sampling distribution of the means and how that is normally distributed? The sampling distribution of variances has a chi-squared distribution. Cool. So this is exactly it. So if we're going to do this, all we need to do is add up all of our observations with all of that stuff. So we're going to have something like 90 minus something over something. I'm just going to say X for everything, even though it's different, because I don't want to have to figure it out. So this would be the something for what we would actually expect for our residents that pass. So it would be this squared plus, what's the next one? 70 minus something squared over something for that particular plus 10 minus something squared, all that jazz, and the next one, 30 minus something over something. All the expected. So how do we figure out what values we should actually expect? So this comes down to like our hypothesis test. What would the null hypothesis be? Well, the null hypothesis would be there's no relationship, right? There's no relationship, which means that it's completely independent whether you pass or fail of whether you're an online student or not, right? It's independent. And we know some things about independence. We know things about probabilities of independent events. If we wanted to figure out the probability of two independent events, getting ahead on one and getting ahead on the next, how do we figure that out? Let's get a chart. What's the probability of getting ahead on one flip? 50. Or 0.5 actually, 50%. How about the probability of getting one coin flip is ahead and the next coin flip ahead? I think we've done this 2 or 3 times in this class. 0.25, right? We just multiplied 0.5 by 0.5. So let's see. Which of these ways is going to be easier to figure this out? What percent of our students are resident students? 50%, or 0.5, right? And how many percent are online students? It's easy, 0.5. Now, if half of our students are residents and half of our students are online, and we have 160 students that pass, how many of those 160 students should be resident? What would we expect it to be? Half of them, right? If residence is independent of whether or not you fail, we should expect the same proportion of students that pass to be the same proportion as the number that are resident or online students. So we can figure this out really easily, especially given the values that I've already done. So if these are our observations, I'm going to shift this over a little bit because I've noticed in some videos I miss a little bit. These are going to be the things that we expect. Expectations. Okay, so we have resident. I'll do it down to res. Online. Pass. Fail. So we have our total here, 160. So 0.5 times 160 is going to be 80. Okay, now let's do it for online. How many should we expect online? 80, and we can do this a couple different ways. One, we can see that, all right, we'll multiply the probability that they're online by the total number that have passed, and we'll get the same thing, 80. Or, once we know that we have 80 here, and we know what the total is, we can just subtract, and boom, we've got 80. Okay, so, how many of our students that fail would we expect to be residential students? 20. And how many would we expect to be online students? 20. So depending on the frequencies and the probabilities, these may not always work out to be the same thing. They did in this example because I contrived it to make it easier to do the numbers for this example. But if this was like 70% and 30%, you would observe different values. But notice in both of these situations, situations, the top row sums up to 160, bottom row sums up to 40, right? 80 plus 80 is 160, 20 plus 20 is 40. Also, 80 plus 20 is 100, 80 plus 20 is 100. So our row and column totals match up. So what we have now, not only do we have what we've observed, we have what we would expect to observe. So, if we substitute these values in, we have 90 minus what? What do we expect for the condition, the resident pass condition? 80. And we're going to put that expected value down here. And what do we have for this condition, the 70? 80. And we expect 80 down here. How about this? 10 minus 20. And 20 down here. And finally, 30 minus 20. And we get 20 down here. So we can add this up pretty easily. So we have 10 squared, right? So that's 100 over 80 plus 10, oh actually that's negative 10 squared. What's negative 10 squared? 100 over 80 plus 10 minus 20, that's negative 10 squared, 100 over 20 plus negative 10 squared, so that's 100 over 20. And we could go through and calculate all this stuff out. I don't want to do that because this isn't a stats class, but I want to show you how we can look at a different type of problem. So previously, with the t-tests, we were looking at interval and ratio scale variables. And we were looking at two particular conditions, right? Are they resident or are they online? How were their scores? Here, maybe we're not interested in their scores ultimately, but just the pass and fail rates. This could be useful for information, or this could be useful information, right? To see if you're failing more students than you would expect to, given the distribution that you're expecting, or given the distribution that the administrators are saying that you should meet if that were to happen. Anyway, so if we did the math, we would get some value for chi-square. And then if we were doing things the old-fashioned way, we would look up that value in a table of chi-square values, given something that is like the number of observations that you have. But in R, we can just do something really simple. We can tell it to do a chi-square dot test, and then give it the data that we're working with, broken down appropriately, and you'll see this in the reading for this assignment. And it will tell us exactly the p-value that would be associated with the chi-square like that. Okay, so we've talked about how to answer questions about two groups that vary on some interval or ratio scale variable. We've talked about looking at two groups and how they vary on some categorical or nominal variable. Let's talk about a different situation. Let's talk about a potential infinite number of groups and how they vary on some interval or ratio scale variable. So don't freak out about a potential infinite number of groups. What I'm talking about really is a correlation. So, how much time? How much time did you spend studying for the exam, Dan? You don't have to tell me the real amount of time studying, just give me something. Minutes.
Minutes?
Yeah.
It was about an hour and a half.
So 90 minutes study. How much time did you spend?
3 hours.
3 hours, so 180 minutes. How much time did you spend?
30 minutes.
30 minutes, oh boy. Hopefully you did well. Hopefully you paid so much attention in class that you didn't need to study that hard.
Didn't go as bad as I thought.
Good. Good. I'm glad to hear that. Anyway, people can spend 3 minutes, 100 minutes, 3.5 minutes, right? You can have an infinite number if you go and become infinitely precise. You can have people all over the place, right? And we could look at their scores. And the scores aren't going to have, an infinite number of possible scores. They're just going to go from 0 to 100 on my test. But we might observe something that looks kind of like this, right? So as people spend more time, they tend to go up. Occasionally you'll have someone who spends a ton of time that does really poorly, but you might also have someone that spent almost no time that does fairly well, right? And so by looking at that, it looks like we have some type of a correlation. It looks like we could draw a line that goes through the data that looks something like that, right? In the mean, to me, it looks like the mean is right about there. Does that seem like the right mean for both x and y for you guys? Or pretty darn close? All right, groovy. So we have some amounts of study time. We have some exam scores. And it appears that we have a relationship between these. So how do we see whether or not there's a relationship? What variable do we calculate? Or what statistic do we calculate?
Is there regression?
We can do a regression, but we haven't talked much about regression yet. What's a regression based off of? So lots of times when you hear about regression, you'll hear MRC. This is regression. And this is multiple. And what's the C? Correlation. Beautiful, thank you. So what we can do to describe the relationship with these guys is run a correlation, which will tell us how well these variables vary together. Remember the whole how much and the how well? So the covariance is how much they vary together, and the correlation is how well they vary together. So based on the correlation, we'll learn something, right? So R, the absolute value of R, tells us what? Is it the strength of the relationship or the direction of the relationship? It's the strength of the relationship. And what the absolute value of R represents is how tightly packed around this line these dots are. And this line is trying to predict our Y variable, or our dependent variable, from our independent, or our X variable. And again, be careful with independent and dependent here, because if we're just doing a correlation, we haven't manipulated anything, so we need to be really careful about making claims of causation. But so what we're doing with this line is we're trying to predict Y from X. And we want to predict a particular line such that these differences, or the squared differences in Y from each of the points around that line is minimized. Think about what the mean does, and how we talked about mean and its relationship to the variance. So the mean, what it does is it's that balance point that minimizes the squared deviations from that mean. The formula for this line will give us Y-scores that will minimize the squared deviations from the Y that we are expecting compared to the Y that we actually observed. A lot of this stuff, very similar in ideas, right? We had observed minus expected. Here, we are making predictions. This is what we are expecting. This is what we're observing. So now, I want to ask a question. Can someone tell me the formula for a basic line? Y equals mx plus b. What does m represent? Slope. Do I need to change that? No, I went up there once, right? Yeah. Slope. And b is intercept. Okay, for some reason, a lot of the ways that people describe slope and intercept in stats books, I find a bit goofy, because I grew up with the whole m is slope and b is intercept. And in a lot of stats books, you'll see something like this, y equals, bx plus a. where A is the intercept and B is the slope. So if you see that, just remember that whatever you're multiplying x by, that's the slope. So when I talk about the slope and intercept on like a quiz or an exam, I won't say M, what's M, or what's B. Actually, M would make sense, but if I said what's B, you'd be like, was that the intercept or is that the slope you're talking about? And I don't want to have that type of confusion, so I'll just say the slope, or say the intercept. So, we have some line. Imagine that we didn't have the points there. Instead, we were just graphing a nice, pretty line. What is the slope? How can we find the value of a slope for any line?
y2 minus y1 over x2 minus x1.
y2 minus y1 over x2 minus x1. And these, it really doesn't matter if you have the 2's or the 1's in front of one another, unless you are talking about 2 is farther along this way, because regardless of the way that you set that up, if you stay consistent, you should get the right thing. Okay, another way of talking about this is the rise over the run, right? Another way of talking about this is delta y, delta x, which is probably scary for some of you, but delta just means change. So the change in y over the change in x. So let's ask ourselves, how much are x and y changing? Do we have any variables or any statistics that tell us something about how much y and how much x change? Oh, I thought you were going to go. Thinking about it. So change reflects some difference, right? Is there anything that tells us how different each observation of x or y is? Or maybe how much different scores of x and y deviate? Because a difference is a deviation. Not covariance. Standard deviation. So, yeah. That's y, that's x. So this tells us the average change in y, right? We have that little n in the denominator. There's something very close to an average change. It's some type of change. So we have some type of change in y compared to some type of change in x. Does that make sense? Now, just because we have a change in y and a change in x, we can't determine what the slope of that line will be all by itself. Why not? Anyone have an idea? Are the changes perfect with one another? As x goes up 10, does y always go up some amount? No, they don't. Well, how well did the changes go together? Is there anything that tells us how well the changes go together? Correlation. Correlation. Think about this. A correlation is, if we think about the formula for it, so we have the covariance of x and y all over Sx times Sy. And what I said before is that this covariance is how much they vary together compared to how perfectly they could vary together. If they varied perfectly together, R would equal 1, and you would be fine just with this, right? You would just have a straight line, and that part would work. But most of the time, you're not going to have a perfect variation, right? And R tells us how well they vary. So if we had something like R equals 0.8, then we know that on average, as there is a change in our x of 1, we have a change in y of 0.8. So very intuitively, we figured out what the slope for a regression line is. So the correlation, all the correlation tells us is how well these two things go together. But knowing how well they go together, we can make predictions. And it just so happens, if you create a line based on this knowledge about how well they go together, you've done a regression. So a regression is the process of coming up with this line that best fits the data. Now the slope of this line is the correlation of x and y times the standard deviation of y, or some type of average change in y, over some type of average change in x, which is just like all these other formulas for the mean. So with this piece of information, we have the ability to almost completely figure out what this equation should be. Sorry, mx. And let me actually write this here. R xy sy over sx times x plus, or r y equals mx plus b. So we've just figured out that this is the slope. Let me get rid of m, slope. How do we find the intercept? Say what?
Set y equals 0.
Set y equal to 0.
I think. I can't remember.
So y equals 0, what's b?
No, make B 0 and solve for y.
Make b 0 and solve for y. Okay, so y is equal to the slope times x. There it is. We've solved it, have we?
No.
How many unknowns do we have in this situation? So we can set things to 0. How many unknowns are there? Well, we know what this is. We know what sy is, right? After we've collected the data, we've figured out what the correlation is, we know what the standard deviations are, so we know this piece, right? What's x? What's y? Oh, weird. What's x, what's y? We have two unknowns. How many equations do we have to solve for two unknowns? Two. Two equations, two unknowns. How many equations do we have? One. Fudge. So, we need to think about this. If the mean of x is the best estimate that we have for what x should be, what's our best 1 point estimate of if we didn't know anything else and we had to guess how much students studied and we had to guess exam scores? And let's say that the average time was, let's say this is 2 hours. Doesn't sound like that's the right average, but. And let's say the average exam score, what was it? I think it was, said you need to add 6, so that's 8. So 75 minus 8, that is 67 raw. So you're going to give me money if I'm within 20 minutes of someone's study time and within 5 points of their exam score. So you blindfold me and you pick out a student. What's my best guess for that student?
2 hours and 67.
2 hours and 67. How did you come up with that?
You took the average.
I took the average, right? The mean of x is the best guess that we have for x. The mean of y is the best guess that we have for y. Does that make sense? So, our line of best fit, if it's really the best line, that line should go through the best point, right? Best line goes through the best point. So if that's the case, we're not going to make b 0. Instead, what are we going to do? So we have this thing, y equals, I'm just going to put slope, and I'm going to use m. That's what we're all thinking about, which is really just this here, and we know what this is. And we need to solve for b. And we now have values of x and y that we can expect, right?
What,
So-
65% or was it?
We just need to substitute in the means, right? So y, the mean of y should equal the slope times the mean of x plus b. So that line should pass through that point. And when you set b equal, I'm sorry, my brain just totally farted. The line should pass through that point. I'm just going to stop there. So what does b equal? This is some plain old easy algebra.
Y minus 7x.
Y minus, actually not just y, but the mean of y, minus m times the mean of x equals b, right? We just subtracted m mean times the mean of x from both sides. Now we've calculated the intercept. That's all that a simple regression does. It takes our data, we look at how much those data vary together, find the covariance, we figure out how much those data could potentially vary together. That's the Sx times Sy, the standard deviations that I had down there at some point, right, on the denominator of the correlation. We calculate the correlation from that. Then the slope is just the average rise over, or sort of average rise over the sort of average run times the correlation, because that it's not probably going to be a perfect rise over a perfect run. And that correlation tells us how much of the rise is associated with that run. So we multiply this, the rise over the run, times the correlation, and then we can use that and substitute in the values for our means to calculate the intercept. And this line, as I mentioned before, this is going to be the line of best fit in the sense that all of the squared y deviations around that line are minimized. We could draw a whole bunch of other lines that go through the same mean, but they're not going to give us that same best fit because now this is really far away. And since we're squaring the differences just like we did in the variance, these differences are going to be really big, right? So again, we are doing something like comparing what we observed to what we expect. And again, I'm not going to tell you how you test the correlation to see if it's significant, because you can do that in stats, but it actually involves a t-test. There's just a t-test, which kind of makes sense, right? The t-test tests to see if two things are related. Is there a difference between, treatment 1 and treatment 2? If there is, that means that there's a correlation between those things. Oh dear, sorry.
You're grounded.
Monday we're going to talk about ANOVAs. Wednesday and Friday, we don't have class. I'm going to be in New York for a psychological convention. That doesn't mean there's not going to be stuff for you guys to do. Part of this is a lab methods course. So I'm going to send you guys some online experiments to participate in, not for extra credit. And they're not going to be anything that myself or my students are going to use for real data. You'll get to participate in several experiments, and when I come back, we'll talk a little bit about them and move on to more complex experimental designs. Have a lovely weekend, everybody. You too.